In this in this video, I'd like to work through the problems that were on our test 2. This is in an effort to help you with the rework and the analysis that are due this Friday. There are 2 parts to this assignment. The first part is to rework each problem that you missed on the test. Now, be aware that some of the problems may have had an X, meaning it wasn't really perfect, but perhaps I wrote -0, meaning it's not perfect, but I'm not going to take any points off this time. You should still rework those problems. Most cases involved a -0 when the answer wasn't fully simplified. The second part of the assignment is the analysis sheet. This is the worksheet. It's 2 pages. You need to complete both pages of that analysis sheet. You may print the sheet and write directly on it, or you may type on the sheet, or you can draw your own sheet as long as it involves the chart in addition to the questions. That assignment is all due on Friday. Let me help you walk through some of the examples from the test. Let's start with question number 2. Using the derivative formula, the definition of a derivative, or in other words, using the limit of a difference quotient to calculate the derivative. Now, I will say as an aside that you could check your answer with just doing the derivative, because we know that the derivative is going to be 2x minus 5, but getting that answer isn't the big piece to this. The big piece to this is really applying the definition. This is what it might look like. We'd say that the derivative of f of x is the limit as h approaches 0 of f of x plus h minus f of x. So f of x plus h, I'm going to replace the x's with x plus h. So we have x squared minus 5 times x, and in place of x, I'm going to put x plus h. And then we're going to subtract from that f of x and divide the whole thing by h. Now, what is that going to look like? We have the limit as h approaches 0 of, now I'm going to apply the pattern for multiplying. X plus h squared is x squared plus 2xh plus h squared. You could also FOIL it out if you need to. And then minus 5x minus 5h when I distribute that negative 5. Another approach, if you struggle with this at all, is to write this polynomial list of terms, whatever you want to think of it as, off to the side over here. And now I'm going to subtract f of x. So I'm going to subtract x squared, and I'm going to subtract the opposite of 5x. So that becomes plus 5x. And if I do that subtraction over here, I subtract x squared and subtract the opposite of 5x. If I do that off to the side, I should get the same thing, but let me finish this out. Remember that we're taking this whole thing and dividing by h. And remember that we're going to do the limit. But what does that become when we simplify it? When we simplify this, this x squared minus x squared cancels out. Negative 5x plus 5x cancels out. Or if we did this vertically, we'd get the 0 plus 2xh plus h squared. The opposite of 5x minus the opposite of 5x is 0, so those cancel out, and minus 5h. But do you see we get the same result here? 2xh plus h squared minus 5h, and the whole thing is over h still, right? So we have 2xh plus h squared minus 5h. Before I do the limit with direct substitution, I still have to divide out this h that's in the denominator. And you can see in this numerator, the purple numerator, 2xh plus h squared minus 5h, that I could actually factor out an h, right? I'd get h times, I'm just doing it off to the sides in case you're not visualizing this, h times the quantity of 2x plus h minus 5. But what I'm doing here is I'm taking this h and dividing it into each of the h terms. So what I'm left with now is the limit as h approaches 0 of, oh, I don't need a fraction line anymore because I've divided out the h. 2x plus h minus 5. And now I'm ready to apply the direct substitution. When I apply the direct substitution, that's 2x plus h minus 5. And in place of h, I'm going to put the 0. So that leaves me with 2x minus 5, which is what I expected by doing the derivative without the formula. I mean, with the formula, without the definition. But I want to highlight that doing this check, although it's a good idea, to get the answer and to get the full credit, you do need to follow the directions which were to use the definition. Let's look at number 3, the sketch. On number 3, you're asked to draw one sketch that demonstrates all 5 of these characteristics. Sketch the graph of a non-constant function with the following properties. So let me show you each one of these properties one at a time. Looks like the highest I'm going to go up is 7. And we're going to need a -3 and a 5 and a pi and a -2 and a -8 and a 4. Okay, so let me highlight each part. Many of you seem to be getting this, but let me make sure everyone's getting this. Or, you know, I'm not going to start there. I'm going to start with the easy part. It's called the low-hanging fruit, right? This easy part is that f of -8 is 7. F of -8 is 7. F of 4 is 7. F of +8, oh, I forgot to put that one on the axis. F of +8 is 7. So those values all equal 7. I also have f of -2 is pi. And f of, that's the derivative of f of -2 is 0. So I still need to manage this piece. Okay, let's go to the limits now. We've got the limit, that didn't show very well, let me highlight it instead. We have the limit as x approaches 4 from the right is -3. So from the right, we'd be coming in over here from this point, it looks like. And as we're approaching from the right, the value of the function is -3. From the left, we have the value of the function approaching 5. So from the left, as x approaches this 4, or I'm sorry, as x approaches 4, the value is approaching 5. The last piece we need is this derivative. So if the derivative is 0, means we're getting something like this, or this. Either one is fine. So now let me just connect this up. And there you have it. Let's just check through each of these different points. The limit as x approaches 4 from the right is -3. The limit as x approaches 4 from the left is 5. F of -8, 4, and 8 all equal 7. F of -2 is pi, and the derivative at -2 is 0, and it's not constant, so it's not a horizontal line at any point in the graph. So that meets all the criteria. Let's try number 4 and 5. Number 4, determine the equation of the tangent line. So the first thing I need to notice is that the slope of the tangent line is going to be equivalent to the derivative. So the derivative, now I'm going to think of this f of x, rather than using the quotient rule, I'm going to think of it as an x to the -1. So the derivative is just -1 times x to the -1 minus 1, or in other words, -1 x to the 0, or in other words, just, oh wait, -1 minus 1, sorry, it's not a 0, -1 minus 1 x to the -2. I'm getting ahead of myself because I know that the slope is going to be -1. Okay, so we have -1 x to the -2, or just the opposite of 1 over x squared, right? So what I want to do next is find the m when x is -1. Find the slope when x is -1. So that's the first derivative when x is -1. So I'm going to take this -1 and fill it in to this opposite of 1 over x squared. The opposite of 1 over x squared. And then in place of x, we put a -1. -1 squared is 1. So we have the opposite of 1 over 1, which is -1. So now what I know for number 4 is that the slope of our tangent line is -1, and I know that we've got this point, x is -1, y is -1. I can use that to find b, y equals mx plus b. So -1 equals -1 times -1 plus b. -1 equals 1 plus b, subtracting 1 from both sides. I'm going to get that b is equal to -2. So I have a slope b of -1. I have a y-intercept, or I'm sorry, a slope m of -1. I have a y-intercept b of -2. I can write the equation of the line y equals -m, so -1 times x, plus b, so -2, and there's the equation. Number 5 is an important question because it gets at this important definition of continuous at a point. So write an equation that expresses that the function is continuous at x equals 3.14 pi. That would mean that the limit as x approaches a, in this case 3.14 pi, of f of x is equal to f at 3.14 pi. And this is what number 5 should look like. Number 6 through 10 or so ask us to do the derivatives. So let's look at each of these derivatives. This first one, I did say that this would be on the test. It's a question that's asking us, it's an example that's asking us to use implicit differentiation. So I'm going to start by using this product rule. The derivative of our product is fg prime plus g f prime, where f is x squared and the derivative of f is 2x. G is y squared and the derivative of y squared is 2y y prime. So when I apply that to number 6, I'd get the first, that's the x squared, times the derivative of the second, that's 2y y prime, plus the second, it's y squared, times the derivative of the first, times the 2x. All of this is a derivative of the x squared times y squared. Continuing on to the other side, the derivative of x is 1, the derivative of y is y prime, the derivative of 7 is 0. Now I need to solve for y prime. So as I look through the equation I have, it looks like there's 2 y prime terms. I'm going to move all the y prime terms to one side. So we've got 2x squared y times y prime, and then I'm going to subtract this y prime, so minus 1 y prime to the other side. And this is going to equal, I still have this 1 here, and I'm going to move this 2x y squared to the other side, so minus 2x y squared from both sides. When I finalize this problem, the last step is going to be to divide this 1 minus 2xy squared, divide both sides by 2x squared y minus 1. That's this part here, because I want to isolate the y squared, right? So to isolate the y squared, I'm going to divide by 2x squared y minus 1, and that's the answer that we get for number 7, or for number 6. Let's look at number 7. The easiest way to approach number 7 is to rewrite it so I can apply the power rule. You could use the quotient rule, but I think you'll find it much easier to write that 3 over x squared as a 3 times x to the negative 2. So the derivative applying the power rule is 2x minus 6x to the negative 2 minus 1, so that's negative 3. The directions asked you to simplify by eliminating all rational and negative exponents. So the final step would be to rewrite this as 6 over x cubed. Number 8, let's do that on the next page. Number 8, I'm going to have to use the chain rule, so I'm going to start with 12 times that whole piece there, right? 12 times everything that's in the parentheses times the derivative with respect to x of everything in the parentheses. So what does that look like? We have, and then it's 12 times everything in the parentheses to the 12 minus 1, which is 11. So we have 12 x to the 7 minus 11x plus 10 pi squared. By the way, 10 pi squared is a constant, right? Minus 9, all to the 12 minus 1, or 11. And now I'm going to multiply this by the derivative of this piece, the inner piece, the piece that's inside the parentheses. So that is 7x to the 6 minus 11. And everything else is a constant. 10 pi squared, the derivative of 10 pi squared is 0. The derivative of 9 is 0. So that's all there is to it, and it's done. Let's look at number 9. For number 9, I need to apply the power rule, and it might help if you think of this as the sine of square root of x squared. So when I apply the power rule, that might be helpful. For number 9, the outer piece is 2 times the sine of square root of x to the first power. So just 2 sine of x. But then I have to do the derivative of sine square root of x. Let me carry down the 2 sine square root of x. The derivative of sine square root of x is now going to be cosine of the square root of x, but then I have to remember to do times the derivative of the square root of x. So we've got 2 sine square root of x times the cosine of the square root of x times, and now the derivative of the square root of x is 1 over 2 square root of x. Do you see that these 2's will divide out? And so I'm left with 1 over the square root of x times sine square root of x cosine square root of x. Or you could write it sine square root of x times cosine square root of x all over the square root of x. That would have been okay also, either way. There's no need to rationalize that radical in the denominator. If you did, then I suppose you'd have x square. So if we did this times the square root of x over the square root of x, we'd have a square root of x in the numerator and an x in the denominator. But there's really no need to do that, rationalizing the denominator. We could leave it in this form. Number 10 applies chaining a couple times again. So we would start with the derivative of cosine is the opposite of sine. And then to chain that, we would then need to say that's times the derivative of the sine of x squared. Let me make sure everyone's following what we're doing. I'm going to highlight the inside. The inside here is the sine of x squared. That's why I'm applying the chain rule by doing the derivative of the sine of x squared. So we have the derivative of cosine is the opposite of sine of this thing that's inside. And then we're going to multiply times the derivative of the thing that's inside. So we have the opposite of sine x squared times the derivative of sine is cosine, so cosine of x squared. But then I've got to do times the derivative of x squared. So putting this all together, we get the opposite of sine x squared times the cosine of x squared times 2x. Now it'd be a little bit more proper, maybe not entirely, but we could usually want to put factors that aren't trig functions in the very front. So we'd have the opposite of 2x times the sine of sine x squared times cosine of x squared. But that isn't absolutely necessary. Number 11, applying the product rule. Let me see if did I save another page? No, I didn't. So I'll just squeeze it in here. For number 11, using the product rule, I'm going to start by stating the rule. Fg prime is Fg prime plus Gf prime. So the product differentiated is the first factor times the derivative of the second factor plus the second factor times the derivative of the first, where the first factor is x squared plus 1 and its derivative is 2x. The second factor is x cubed plus x squared plus 1 and its derivative is 3x squared plus 2x. So applying the product rule, I get the first, so it's x squared plus 1, times the derivative of the second, 3x squared plus 2x, plus the second, see, x cubed plus x squared plus 1 times the derivative of the first, 2x. The directions did say to simplify this. When you simplify this, when you combine the like terms, multiply, so FOIL, distribute, combine like terms, we'd have 5x to the fourth plus 4x cubed plus 3x squared plus 4x. I'm going to skip showing that algebra right now, but work through that and pause the video if you need to get that a little better. Number 12, we've got to use the quotient rule. So f over g prime is fg prime subtracted from gf prime all over g squared. So what that would look like is let me write f and g. F is x minus 1, and the derivative of that is 1. G is x squared plus 2x plus 1, and the derivative of g is 2x plus 2. So g times f prime is just 1, minus f, it's the numerator, times g prime, the derivative of the denominator, all over g squared. Now, take note that I could factor this denominator, x plus 1 squared, right? When I square the denominator, I'm going to get x plus 1 to the fourth. The reason I mention that is that when you simplify this numerator, so distribute or use FOIL over here with the x minus 1, 2x plus 2, subtract it. So make sure you distribute the negative after you FOIL. And then you're going to be able to combine some like terms and factor. And after you factor, you would be left with, let me just show some of the steps. I'm skipping some steps here, skipping some of the algebra. After you factor, it would look like this, and then you could reduce. So I'll leave it there for you to finish from that point, but you should be able to then reduce one of the x plus 1s. So it'd look like this, but this work in between is all algebra. Number 13, to use the chain rule, y prime is going to be 1 over that square root times the derivative with respect to x of the radicand. So what does that look like? 1 over, and it's 1 over 2 times the square root. 1 over 2 times the square root of 6x5 plus 4x cubed minus 2x times the derivative of the numerator, 30x4 minus 12x squared minus 2. And that doesn't need to, it actually, you know what? I was going to say it doesn't need to be reduced or doesn't need to be simplified, but it does have a factor of 2 that you can divide out. So be sure that you simplify by factoring out that 2. Number 14, the easiest approach to number 14 is going to be to rewrite as a power rule. 14 is really easy after you do that. So 5x to the 4 fifths plus 12x to the 2 thirds plus 4x to the 1 half minus the cotangent of x minus the tangent of x. When you do that derivative, the answer is going to come out to be 4 over the 5th root of x plus 8 over the cube root of x plus 2 over the square root of x plus the cosecant squared minus secant squared. I'm going to leave that for you to finish there. Number 15, it's another example, again, of simplifying first. I know I wrote that kind of funny, didn't I? But maybe you see why. This x squared is x times x, and then I broke the x into a square root of x times the square root of x. The reason I did that was I wanted to show you that we could reduce one of these x's right off the bat. So once I've rewritten it like this, I could now rewrite this using rational exponents. So that 6 over the square root of x is 6x to the 1/2. X times the square root of x, that's like x to the 1 times x to the 1/2. So it's x to the 3/2. From here, apply the product rule and simplify, and you'd get this end result. I'm skipping some of the algebra here, and I've skipped the power rule, but you should be able to get from the rest of that from the work that I've shown here. If you do need extra help, I'm more than happy to help, so please let me know. I just don't want to go too long on this video if we can avoid it. For number 16, we have a polynomial, and so if you recall, then the process here is to find the lead term. So what we have is the lead term is the negative 5x. So what I have is that the limit of this whole polynomial as x approaches infinity is going to be equivalent to the limit of negative 5x to the 8th as x approaches infinity. The limit of negative 5x to the 8th would be that infinity to the 8th is infinity, and the negative 5 times infinity is still an infinity, but we keep that negative, so it's going to be negative infinity. Number 17, using direct substitution, we'd get 3 times negative 2 squared plus 8 pi. So that's 3 times 4 is 12, 12 plus 8 pi. Number 18, the sine of 74 pi. If I'm going to do the limit as x approaches in a pi, do you notice that this was a little bit of a trick question? Not so much a trick question, but a question that's saying, hey, are you paying attention to what a limit is? There's no x in here because the sine of 74 pi is a constant. So the limit as x approaches pi is just the sine of 74 pi. Now, from the unit circle, we know that if it's pi, any factor of pi, the sign is 0. Sine of 2 pi is 0, the sine of pi is 0, because it's the y term, right? So this is 0, but some of you got the 0, but you kind of guessed at it, or you were applying a limit in a strange way. What you really needed to show to get the full credit was that you recognize that that was a constant. For number 19, this is applying that new limit technique. So that's that the limit of sine anything over the same anything as x approaches 0 is going to be 1. So for number 19, we want to build, let me erase this so that we have space here. We want to build sine box over box, right? We have sine of x over x, but we have this extra 14 in here. So you see what I can do is I can simply pull out that 1 over 14. the limit of sine x over x is just 1. 1 times 1 over 14 is just 1 over 14. Number 20, this one's a little bit trickier. I'm going to rewrite it like this. You see, what I really want is a 5x underneath that sine of 5x, right? There's a couple approaches you could take here. Here's one approach, is just put that 5x in here and then put it here. And you'll see that you'll see that we end up with a 5 over 2 there. That approach doesn't quite match up to what we had been doing, but it does work, because what we get here is oh, sorry about that. I thought I had the highlighter on. The sine of 5x over 5x turns to a 1. The x's divide out, and we just get 5 over 2. But, and that's the answer, the 5 over 2. The way we were doing this before will also work. So let me squeeze this in here. We have a 5x over 2x, and we're trying to think of what can I multiply 5 over 2 times to get 1. And the answer is going to be 2 over 5. So if I multiply this by 2 over 5 and then counter that with a 5 over 2, it's going to give us the same result also. So try that a little bit more, practice it, look at the other examples that we have, and I think you'll see it work out. Just in case you didn't fully get that, let me finish this out. That these 2's would divide out, and now we have our sine 5x over 5x, which goes to 1, and then our result 5 over 2. I hope that this video helps. Please let me know if you need further help with any of these types of examples.